Welcome to our lesson on derivatives in calculus. In this video, we'll introduce the concept of the derivative and understand how it works as a function. So what exactly is a derivative? The derivative of a function measures how the function's output changes as its input changes. Essentially, it's the instantaneous rate of change of a function, or the slope of the tangent line at a specific point on the curve. Think about a car's movement. The position of the car is a function of time. The derivative of this position function gives us the car's velocity at any moment, which is how fast the position is changing. Let's introduce the formal definition of the derivative. The derivative of a function f at a point x equals a, denoted as f prime of a, is defined as the limit as h approaches 0 of the fraction with numerator f of a plus h minus f of a and denominator h. This fraction represents the average rate of change of the function over a small interval. As h gets closer to 0, this average rate approaches the instantaneous rate of change at point a, which is what the derivative gives us. Geometrically, we can understand this as the slope of the secant line between 2 points approaching the slope of the tangent line as the points get closer together. Now, let's think about the derivative as a function itself. If we apply the limit definition to every point in the domain of our original function, we get a new function called the derivative function, written as f prime of x. The derivative function, f prime of x, equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h, for every input x. The derivative function tells us the slope of the tangent line to the original function at that point. This gives us a powerful tool to analyze how a function behaves. Let's work through some examples to see how we calculate derivatives using the limit definition. For our first example, let's find the derivative of f of x equals x squared. Step 1. We write the difference quotient. That's f of x plus h minus f of x, all divided by h. Step 2. Substitute our function into this expression. We get x plus h squared minus x squared, all divided by h. Step 3. Let's expand the numerator. X plus h squared equals x squared plus 2xh plus h squared. Subtracting x squared leaves us with 2xh plus h squared in the numerator. Step 4. Now we divide everything by h. This gives us 2x plus h. Step 5. Finally, we take the limit as h approaches 0. The term h goes to 0, leaving us with 2x. So the derivative of x squared is 2x. For our second example, let's find the derivative of f of x equals 3x plus 2, which is a linear function. Again, we start with the difference quotient. We have f of x plus h minus f of x divided by h. Substituting our function, we get 3 times x plus h plus 2 minus 3x plus 2, all divided by h. Simplifying the numerator, we have 3x plus 3h plus 2 minus 3x minus 2. All the terms cancel except for 3h, leaving us with 3h divided by h, which equals 3. Taking the limit as h approaches 0, we get f prime of x equals 3. This makes sense because the derivative of a linear function is its slope, which in this case is 3. The constant term 2 disappears when we take the derivative. For our third example, let's find the derivative of sine of x. This is a bit more complex, and we'll need to use some trigonometric identities. We'll use these two key facts: the limit as h approaches 0 of sine of h divided by h equals 1, and the limit as h approaches 0 of cosine of h minus 1 divided by h equals 0. Starting with our difference quotient, we have sine of x plus h minus sine of x divided by h. Using the sine addition formula, sine of x plus h equals sine of x times cosine of h plus cosine of x times sine of h. Substituting this into our difference quotient, we get sine of x times cosine of h plus cosine of x times sine of h minus sine of x, all divided by h. Rearranging the terms, we get sine of x times the quantity cosine of h minus 1 divided by h plus cosine of x times sine of h divided by h. Taking the limit as h approaches 0, the first term becomes sine of x times 0, which is 0, and the second term becomes cosine of x times 1, which is cosine of x. Therefore, the derivative of sine of x is cosine of x. Now that we've seen how to calculate derivatives, let's interpret what they tell us. If the derivative is positive at a point, the function is increasing there. If the derivative is negative, the function is decreasing. And if the derivative equals 0, the function has a horizontal tangent, which could indicate a maximum, minimum, or inflection point. Here's a summary of some common derivatives that are useful to remember. The derivative of x to the power of n is n times x to the power of n minus 1. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of e to the power of x is e to the power of x. And the derivative of the natural logarithm of x is 1 over x. The derivative is a powerful tool in calculus that helps us understand how functions change. In future lessons, we'll explore more applications and techniques for calculating derivatives. Thanks for watching.